Thanks for having me here for the opportunity of presenting my lab's work about differential privacy and application in the network traces. So I'm Zhou. I'm currently in UC Irvine, directing the UCI DSP lab, and was a joint work with my students, Dan Yusun, she's from UCI, and my collaborators from SDSU and UVA. The paper was published last year at ACMMC. So I'm going to talk a little bit more about what we do from that project. Um, okay, so I'm more like a network person, network security and privacy person. So I really care about network applications. So what we found of lots of those network applications is like they do things like optimizations, anomaly detections, and predicting the network features. Most cases, they need the data to train a model for the predictions and anomaly detections. So the data are typically in two sources. The first is the net flows. You can actually capture those things from the firewall, from the proxies, and you have those IP5 tuple, like source IP address, destination IP addresses, port numbers, and the protocols and timestamps. Another source is called network packets. So they are more fine-grained. They have headers from the two layers, layer 3 and layer 4. My impression is like 20 years ago when I tried to do the research in this domain, we always have the issues like we don't have the data. Where can we find the data? My feeling is nowadays the issue was kind of resolved with more parties sharing the data, like from the research networks, ISPs, some really good parties sharing the data, like UIC, who manages the DSP routes, and the UCSD KAIDA. So they collect lots of network traffic and they share with researchers. That's good. But if we share the data, then naturally that comes with privacy risks. So I want to point out one really interesting paper published in 2021. So the researchers, what they're doing is they look into the data shared, collected in their networks of the B routes. So it's the DNS logs. They look into this 1 week of data. They found even if they do the appropriate, privacy protections like anonymized IP addresses, by just keeping the prefixes, but still the prefix still leak the information. Okay, so an example here, I think that's really interesting is when they're looking at the IP prefixes, and they found that there is one like DS records relevant to the MX records, which is about email sending and receiving, and that comes from a person from a school named Jefferson Parish, and it's destined to the ICE of DHAs. So I think in the current situation, it's probably more problematic to learn those information. So that's some privacy issue there. Um, so to deal with those privacy issues, even after data anonymization redactions, there has been a paper, which is really good paper published in 2022 on ACMC.com. It's called NashShare. So they try to apply the deep learning models to process the data to make it, more privacy preserving. So the idea here is if I am data providers, I want to share network traces. Okay, so I put it through this generative adversarial networks like GAN, and then I get the results, which is a synthesis traces, and I share with my data consumers. So in this procedure, none of the raw data are shared. It's just another copy of the data with essential features of the original data. So it's a really cool idea. But it turns out the GAN approach don't really have the privacy guarantee. So they still leak sensitive informations. It's actually a really active research domain in terms of how we can develop the methods to infer sensitive information from the data. Then there are two prominent attacks. One is about reconstruction from the synthesized data, and another is the membership inference attack. So both of them are surely effective if you use the GAN model to synthesize the data. So as a more privacy preserving person, then I'm thinking about like what could be a good solution. And the number one solution coming to my mind is like, okay, so how about we play differential privacy on the data? I mean, we can do that on the outcome of the data. Algorithms. So a quick walkthrough of how DP works. Let me give this example. So assume you have data sets with three users contributing, and then you apply the DP randomized algorithms, adding noises to the outcomes to the other people's queries. So you get some answers to that. And after that, say if you remove one users from data sets, and then you apply the same kind of the DP algorithms, the output shouldn't have the statistical differences with the first query. So that's a guarantee of the DP. So by doing that, we try to confuse the adversaries. We want to bound what they can learn from the data outcome. The standard noises of the DP are like Laplace noise and Gaussian noises, and there are lots of mathematical proofs from that. So then, like we have the DP, we have the GAN. How about we combine those two things together? Are we able to get the good synthesis data with both privacy and utility guarantees? So actually, in the paper of NetShare, they play that. They apply the DPSGD algorithm on top of the GAN. So DPSGD, what they do is to add noises during the training procedure on the momentum and then clip the results after noises. And the proof, the DPSGD paper prove everything outcome from the model is DP protected. But it turns out from even the paper, the data utility is a problem. So the authors measure the outcomes without DP in terms of the Earth move distance, which is a measure we try to count how much difference from the original data and synthesize the data, which is like 0.1. But if you add DP noises, even just really like small DP noises, which is opposite to the value of epsilon, that's the privacy budget. So you have really little noises, but still, if you want to fulfill the DP guarantee, the results will be much different from the original results, raw data you have. So we want to do better on that. Uh, when we look at the direction, like initiated by NetShare, what they are doing is the GAN plus DPSGD, and we look at the background of those lab research. Usually, this research does really well on image data sets, but network data sets are different. They are records, they're tabular, they are high dimensional. So if you want to do the DP on network data sets, you're gonna have to add excessive noises to fulfill the DP requirements. And if you look into the synthesis directions, there's another direction which is called a marginal table plus DP. So the idea here is we don't use the GAN or the other deep learning models to synthesize data. We firstly generate the marginal tables to capture the underlying distributions of the original data. So it's more like a sketch of the data. And then we add the DP noises on the sketch, the marginal tables. And then from there, we try to replicate records, synthesize more records to fulfill the marginal tables. So we still make sure the underlying distributions are well captured. In the meantime, we're able to get those data records looking realistic. It turns out this direction works really well for the tabular data. And actually, our solution is based on another work named Privacing. That was also developed by our collaborators at UVA, and they run this system. They do the computation called NIST 2018 DP Synthetic Data Challenge, and they got second place. And actually, the first place is on the same direction, the marginal table plus DP. So we are really motivated to do that. So we take this direction and then we implement a solution specific for network traces. So our idea at a high level is we take the raw traces and then we select the marginals. And I'm going to explain what marginal looks like in next slides. And then we get those one-way and two-way marginals, their combinations, and then we add noises. In our work, we do the Gaussian noise. So we're going to have some noisy marginals, and then we synthesize the records from those marginal tables. So in the synthesis procedure, we make sure the records, after we generated them, and then we go back to get their marginals, it should match the noisy marginals as much as possible. So with that, we can fulfill the DP guarantee. So example about how we do this procedure here is I try to make it really simple, but in the real world data sets, it's more complex. We have more records, more columns. But let's just get one example with two columns, a few rows here. So in this example, we have the destination port column and then the type of the column, which is about decision on network appliances on the records. So in this case, we try to detect if this is normal traffic or attack traffic. So we have a few rows. And through our approach, we're gonna generate some marginal tables, which, and here I just show one two-way marginals. So it's a combinations of different values, and there are a number of rows in the original tables. So you may find the count here is decimal number, but that is because in our algorithm we massage different marginals with overlapping attributes, and we do the average. So it's a weighted averaging. So we're gonna see some decimal numbers. And after that, we add DP noises on the marginal tables instead of original records. And then we kind of round it up to the integer values. And then we try to synthesize the records that matches the marginal tables we have after DP protection. So with that, we can fulfill those DP guarantee. So due to the time limits, maybe I will just spend some time to talk about, I mean, the some parts of the techniques we develop along the way, and then there are lots of detail in our paper. So first, in terms of the data pre-processing, there's something special for network data. Is like lots of the fields, the network traffic, they have large domain sizes, which are represented by the difference between the max value and the mean values, or the number of unique values. So the domain size is typically a big headache, I would say, for the DP algorithm because the noise is always proportional to the sensitivity of the data. And sensitivity of data is just basically relevant to the domain sizes. So if you have large domain sizes, you have to add a large amount of noises. So we try to address this problem by doing the value binning. So we try to cluster the values based on their ranges, continuous value ranges, and then so we're gonna have a smaller domain sizes, and then we can have smaller noises to add. So we try to do the binning differently for the IP, port numbers, integer values, timestamps, and categorical values. So with that, we can tailor our, so that part requires more expert, decision in terms of how we add noises, but it turns out the results much better if we don't do the binning. And another problem we are dealing with is the marginal selection problem. It's actually you can select just the one marginal if you have 10 attributes, and or maybe hundreds of marginals if you do the order one-way and two-way marginals. But the choices can have a big differences in terms of arrows you have. So why this is the case? Like if you select one marginal, you're gonna have to add noises to this marginal. So you have select more marginals, you add more noises, and you're gonna have the noise arrows. But on the other time, if you select less marginals, you are not be able to capture the entire distribution of your whole data sets. So in the extreme cases, if I have like 10 attributes in my data sets, I select just one two-way marginals. So I only capture the relation of the two columns. So then I'm gonna miss the information of the other 8 columns, and clearly that's not acceptable. So you don't want to select too few marginals. So we try to solve the balancing problem with this optimization equation. So in this equation, we have two parts. The marginals we selected are the noises and arrows, and the marginals we don't select that causes the dependency arrow. And we try to play with different combinations, and we try to optimize for the best results. Okay, and the third component that is important to our approach is called record synthesis. So in this case is say if we have the noisy marginals, we try to build up the records that matches with noisy marginals. Can be 10 different marginals. Our solution is called GAMI, which is short for the gradually update methods with marginal initialization. That's the extension of the original GAM methods from private. So our idea here is we want to speed up this procedure. I mean, it's actually really slow if you look at original GAM paper, the privacy paper, because if you have say 10 marginals and you keep playing with adding records, replacing records, and in the meantime, you want to make your synthesized records to fulfill the 10 different distributions. That's actually really challenging. If you want to start from some randomized data sets in the beginning. So our idea is we try to fix a few really important columns in the beginning to make sure they're always preserved, and then we play with the other columns. So that's a part we call as the marginal initialization. So we select some target attributes, and then we play the mean cost flow algorithm, which is a really classic algorithms, and we keep replacing and replicate existing records until we get as close as possible with all those noisy marginals. So these are the some key components we have. And then I'm just going to briefly go over the experiments results a little bit and then some of my thoughts of this line of work. So we play our algorithms, the system on the five different data sets, two packet data sets and three flow data sets. We compare our methods with net share and the PGM and the private MRF. The later two algorithms are also similar as our direction that they do the marginal table selection and then the noises. And we use this default privacy budget, which is epsilon equals to 2. So in terms of the results on machine learning classifications, we found the data synthesized from our systems. NetDB has a close results with the raw data. So what happens is uh, we have the raw data and then we let it to go through the four different synthesis methods, NetDB, NetShare, PGM, Priv, MRF, and we train on the subset and we do the testing on the other subsets, which is the classification. We run through five different models, and if the results of the classification is closer as possible as raw data, then that's best. So it turns out we are the leading algorithm, and the net share, which is based on the GAN and the DPSGD, has the lowest results in terms of accuracy. So in general, this direction looks promising. Um, we also, evaluate the running time of the different methods. It turns out our running time is smallest, and we actually are 2.5 times faster than what the other baseline models. And we believe this is especially important if you have large data sets. You want to save time, right? And then to do the other works. So to conclude, we found the network traces can actually expose some, privacy leakage, and we try to protect it with the approach of synthesize the network traces with the differential privacy. And we compare with the other methods, we found we can achieve better utility in the downstream tasks like machine learning classification, and we are also faster. So some of the future work we are doing and prepare to do. At least a few, but just to highlight the two major things ongoing here is first, we don't really spend too much time in capturing the temporal patterns. So some of temporal patterns is like, for example, if you every day you woke up, you always go to cnn.com to see the news, and later you go to check your Gmail. These are temporal patterns. Some of the temporal patterns are really useful for machine learning, but so far we are not able to capture them. And in terms of downstream tasks, so everything so far we do is more about the table or columns. But there are graph-based systems that has been really useful for the network applications like anomaly detection. So you have to do something more in terms of tailor to those applications. So we're also working on that in terms of how we optimize our algorithms for those more interesting and novel applications. The last thing I want to talk about is my thoughts of those more general direction is like how we synthesize the data and the DP guarantee. So my feeling is the solutions firstly has to be domain adapted or modality adapted. So different solutions may be needed for the image, text, audio, and table separately. It turns out it's really hard to have one solution, one size to fit all. So you have to do some development in terms of adapting the DP approaches. And I also believe we need a new benchmarks and utility privacy metrics for in the real world applications. That would be something moving beyond the theoretical development of the DP. And finally, you may be really interested in the combination of the large language models or foundation models with DP. And in terms of the questions like, can we synthesize something by asking the foundation models and let it give us an answer. And we also have privacy protection. The previous talk has been talking about the privacy issues in large language model memories, and I believe that's also the same issue, a relevant issue here. So I know some work has been done by the other companies like Microsoft, and I think that's interesting. So I just want to bring it out. So what they are doing is called this thing called a private evolution. So they assume you just need to have the black box IP access. So you query the large language models and to address the privacy issues and the large language models, sample some nearby data points of the answers. And they have this histogram and the noises to the histograms and give you the results after the voting. So there has been something going on there, and I really like this line of research, and hopefully there can be more things coming out of there. This is my last slides, and thank you for your time and listening to my talk. And I have the link and my contact information there, and I'm happy to answer any questions.